So today we'll discuss about one more classical problem for process synchronization is the reader writer problem. This classical problem is the nature of this problem is slightly different from the producer consumer problem. In a producer consumer problem, the producer go on producing while the consumer consumes, and you have a bound or a buffer has a particular limit that how many items at a time can be produced. This is another kind of problem called the reader writer problem. The reader writer problem says there is a data set. The data set is shared by two types of users. Correct? The data set is shared by two types of users. One kind of users are called readers. Another kind of users are called writers. So the peoples who only read the data item are called the readers, and those who wants to modify or alter the data in the data set, they are called the writers over here. Okay. So the readers only read the data set and they don't perform any updates. And the writers can both read and write. Correct? And you already know that whenever a writer is writing or whenever somebody is updating the data, that means he is in the critical section. No other writer or reader should enter to the critical section at the same time. Do you agree or not? Whenever a writer is modifying some data in a particular code, section of code, that is the critical section, because at the same time, no other reader or writer should be allowed to enter into the critical section. Do you agree or not? Hello?
Yes.
Okay, suppose one reader is there in the critical section. One reader is there in the critical section. Do you allow the other readers to be in the critical section at the same time or not? Will you allow or not? If one reader is in the critical is in the section of code where multiple readers are reading, can multiple readers be allowed at the same time or not? Can anyone answer? Will it be any difficulty if you allow multiple readers to read at the same time? Anyone who can answer? As
Can you please tell the question again?
the question is that when a writer is writing, we must not allow any reader or writer to enter into the critical section. But can we allow multiple readers to read at the same time?
Yes, sir.
Yes, sir.
Because readers do not perform any updates, therefore we should not make the reader wait while when multiple readers wants to read the data items. So problem is something different. Problem is that we'll allow only one writer to be in the critical section at a time, but we'll allow multiple readers can perform the read operation at the same time to the critical section. So problem is slightly different over here. So allow multiple readers to read at the same time. Only one single writer can access the shared data at the same time. There are two variations of the reader writer problem. There are two variations of the reader writer problem. We may give emphasis to the reader. That means all the readers should finish reading. Then only the writer could start writing. Or we may give emphasis to the writer that whenever a writer is making a request will give emphasis to the writer. At the same time, no reader can enter. So the first variation is of the reader writer problem is no readers will be kept waiting. That means we are giving emphasis to the reader. No readers will be kept waiting unless a writer has already obtained a permission to use the shared object. That means no reader should wait for other readers to finish. That means readers will be given chance to enter into the critical section. Writer may have to wait at the same time. The second variation of reader-writer problem is if a writer is waiting to access to the object, no reader may start reading. That means we will not make the writer to wait. If the writer wants to write, immediately it will be given the access and the reader has to wait at the same time. So there are two variations to this reader-writer problem. We are now going to solve this first variation. Can you say that in the first variation, if you give emphasis, to whom we are giving emphasis? To the readers we give emphasis. In second variation, we give emphasis to the writer. Now, can you tell whether the starvation will occur in these cases or not? In the first case, second case, or both? Can anybody say whether the starvation will occur or not?
Yes, sir, occurs.
How do you say that starvation occurs in the first case? Because we are giving emphasis to the reader. If readers will not finish their reading, the multiple readers are there and they are not finishing their reading, the writer goes on waiting like that only. Even if it is ready, it cannot write because readers has not finished his reading. In the second case, if we give emphasis to the writer and writer takes a lot of time for multiple writing, though then writer may also have to wait. Readers may have to wait in the second case. So in the first case, the readers may starve, and if you go for second case by giving emphasis to the writer, the readers may also starve. Is that clear? Is it understood or not?
Sir, if the reader is in waiting state, then will the writer be also in the waiting state?
No. Yes. When a writer is in the critical section, we are allowing only one writer to write into the critical section. So other writers will also be in the waiting state. Readers will also be in the waiting state. But in the first case, no reader will be in the waiting state. Only writer will be in the waiting state. Is that understood?
Yes, sir.
Now we are going to solve the first kind of solution, first reader writer problem. Okay. So see over here. The solution the following. So we will take what? We'll have some shared data which will be shared by both reader and writer. What is that? First thing is the data set. Both reader and writer wants to access the data set because they don't have access. So what are shared data? The shared data is what? The data set is shared data. We'll take a mutex. You must have remembered what is mutex? Mutex is what? What is mutex?
Binary semaphore.
Mutex is binary semaphore. Correct? So it is initialized to 1. So we'll take a binary semaphore mutex, which is used as mutual exclusion object that synchronizes access to the resource query. So the mutex is initialized to 1, which is used to ensure mutual exclusion when read count is updated. So we want what? We want mutex to be 1, initialized to 1. We'll take another semaphore is write. It is a variable. Do remember these are integer variables. So write is a semaphore which is also initialized to 1. That means this is also a binary semaphore. The write is also a binary semaphore. Mutex is a binary semaphore. And we take another counting semaphore, read count. Read count will take, which is initialized to 0. Read count y will take to count, to keep track of how many processes currently reading the object. Suppose one process enters, will increase the read count. Another process enters, will increase the read count. So every time a process enters into the critical section, will increase the read count. Whenever any one of the process comes out of the critical section, will decrement the read count. So each time a process comes out of the critical section, we decrement the read count. These are the 4 things that need to be shared among both the processes. I hope it is understood. Now it comes to the code. This is important. Just look over here. The left hand side that you can see is the code of the writer. The right hand side code that you can see is the code for the reader. Correct? Now let us see that what a reader should do. What is your objective? Objective is that whenever a writer is writing, that time it should not allow any reader or writer to enter into the critical section. This is very simple or not? Whenever a writer is in the critical section, any one of the writer is in the critical section, it should not allow any other reader or writer to enter into the critical section first. Second one, we should not make the readers wait if no writer is writing. That means if none of the writer is there in the critical section, we must allow the readers to read. This is our objective. Let us first understand the writer. Whenever a writer wants to enter into the critical section, this is our critical section actually. Whenever he is writing, that is the critical section, right? What it does, it simply write a wait over here and signal over here. And what is write? Write is a binary semaphore. So what is the value of write? What is the value of write initially?
1.
1. So it is 1. So what is wait function? Wait function we already know. While s less than equals to 0, do nothing. While s less than equals to 0, do nothing. Otherwise s minus minus and continue. Is it or not? You must have remembered this wait function.
Yes,
okay. So it will, while s less than equals to 0, it doesn't satisfy. It will enter into the critical section, correct? And when that process is in the critical section, that time no other process can enter for writing because write has changed to 0. Because the write has changed to 0. Correct? Whenever a writer has finished his execution, writing is performed, while coming out, it will invoke the signal function. What the signal does? S++. So write is incremented again 0 to 1, so that it will allow the next writer to write. So this is the structure of the writer problem. There is no issue over here, because before writing it is putting a lock by invoking the wait, and while coming out it releases the lock by giving the signal. Correct? But this is for, that means we are ensuring that whenever a writer is writing, that time no other writer should enter into the critical section. But now we'll look into the reader. Whether reader could enter at the same time or not. So we'll go for that, but look into this reader's code. In reader code, try to understand the way I am explaining, just look into that only. There are many lines are written, just look over here. What we'll do, every time a reader will enter, what it will do, it will increment the read count. Whenever reader wants to read, because we will not stop the reader for reading. So we'll increment the read count, right? We will increment the read count. So look over here, we are incrementing the read count. I will tell about the other instructions, just remember. So increment the read count. If it is the first reader, try to understand, if it is the first reader, that means if read count equals to 1, initially what is the read count? Read count initialize is to 0. Read count is initialized to 0. So now it is 1. So 1 means this is the first reader. So if it is the first reader, put lock on, that means put lock on the write WR. If it is the first reader, it will invoke the wait write. It will invoke the wait write. That means write is 1, wait function will make it 0. That means at that time, no other writer can enter into the critical section. Is it understood what I'm saying? Is it understood up to these 2 lines only? I am explaining only these 2 lines. I will explain the other lines. It says that suppose in a room, inside the room is a critical section. So there are many people can go into the room for reading. So whenever the first person will enter, it will put a lock for the other writers. It will put a lock for the writers whenever the first reader enters. Is it understood what I'm saying? Let us take an example to a room. Either the boys, whenever a girl will enter, it will put a lock that no boy can enter into that room. Right? So whenever the first girl enters, there are multiple number of girls may enter into that room. So whenever the first girl will enter into that room, it will put a lock that occupied. Occupied for, it is already occupied, no entry for boys. So what will happen? So whenever a boy will come, it will see that the wait, it has to wait, it will see the right, and it cannot enter because it will spin on the condition itself. Is it understood for these 2 lines, or anybody having doubt? Only this I am saying. Read count plus plus, if read count equals to 1, wait write. Anyone having doubt over here?
Sir, can you explain again?
Okay. See, I have a data set, right? To the data set, either the a reader may come or writer may come. It says that at a particular time, there might be multiple readers. There might be multiple readers over here. R1, R2, you can have multiple readers over here. But whenever a writer comes, no reader or writer would be there. So writer part we have already over. So how will you allow the multiple readers? And second thing is that whenever a reader is there, no writer should come. Suppose the first reader came. Whenever the first reader will come, it will put a lock for the writer. It will put a lock for the writer that no writer should enter into this. It has not put lock for reader. It has only put the lock for the writer. Because we have written wait write. What is write? Write is initialized to 1. Wait function means while s less than equals to 0, it satisfies. Enter it. So sorry, while s less than equals to 0, it will go over there. S minus minus. That means write minus minus. It will make it 0. So once it is 0, that means no other writer can enter at that time. They will find that write is 0. It is spinning over there only. Now, but it has put a lock for the writer, but the reader is not invoking. Are you checking the write in the reader section? You are not checking for write in the reader section. You are not checking write in the reader section. The reader is not checking for this semaphore. The reader is nowhere checking for this. You don't have wait. This wait write is given only once whenever the first reader came. When the second reader will come, or lock has already put for the writer. The lock has already put for writer. That means only the read count will increment. The next reader will come, read count will increment. Next reader will come, the read count will increment. And you have already put a lock on the writer. The writer is, if any writer is coming, it is waiting over there. Where it is waiting? It is waiting over here. If the writer is coming, it has to wait over there. It is spinning over there. But if a reader is coming, it is just incrementing the read count. It is just incrementing the read count and getting into this, and reading is performed. This is nothing but the critical section that you have defined. Is it understood up to this? Now, the question is that when you are doing these operations, try to understand, incrementing the read count, and if it is the fast reader, put the lock on the writer. Increment the read count, as the example that I have given, in a room, whenever a girl will enter, the first girl will enter, it will put a lock for the boys. And the next girl will enter, it will only increment the read count. The next girl will enter, it will increment the read count. But the lock has already been put for the boys, for the writer. Understood? So that operation is this one. So who has put the lock? Only the first girl or the first user reader has put the lock. Is it understood? Now these operations, when this read count is incremented and the first lock will be put, between these, we must not allow the writer to enter. So therefore, we'll put a lock over here, wait mutex, and while coming out, we'll put a signal mutex, so that this will be executed indivisibly, right? We'll put a lock, do all these operations, read count plus plus, read minus minus, and we put a lock on the writer. And once it is done, we'll release the mutex. So that is the reason for which the mutex is taken. So to increment the read count, putting a lock on the writer, these two operations has to be indivisible. Therefore, we put a lock over here and we release a lock over here. We release the lock once the updation on the read count is over. That is the only reason for this wait and signal is given. Okay. So now multiple users are entering into this critical section. Because first reader will come, it will increment the read count, enter, and put a lock on the right. Second reader will come, only increment the read count. Third one will come, only increment the read count. Right? Do remember, when one reader is incrementing the read count, can another reader increment the read count or not? Anybody who can answer? Whenever one process is incrementing the read count, at the same time, can another process increment the read count or not? Anyone who can answer? Whenever one reader is entering and incrementing the read count, at the same time, can another reader enter and increment the read count or not?
No, sir.
Yes or no?
No, sir, because the mutex has already been 0.
Very good, very good. So multiple readers may enter into this critical section, but before entering, it has to execute this code. But before this code, I have put a mutex. So it will execute on the mutex. That means no two reader is updating the read count at a time. Multiple reader will enter into the critical section, that is there. But one by one, they will be entered. One by one, they will be entered. It is not that the gate is open and 5 people enter at a time. One people will enter, it will increment the read count. Second one will enter, it will increment the read count. Correct? So once first one will enter, read count is updated, the signal mutex is done. Then the second one will come, invoke the wait mutex, then its operation is done, then signal mutex. Correct? Now, suppose 3 or 4 people have already entered. 3 or 4 processes has already entered into the critical section for reading. For reading, that means they are the readers. When a reader is there in the critical section, can a writer enter? Can a writer enter? No, because we have first user, first reader has already put lock for the writer. Correct? So writer cannot enter at the same time. Earlier we have ensured that whenever a writer is in the critical section, no writer can enter. So we are ensuring over here that whenever reading is done, when some readers are there, no writer can enter. Correct? Okay. Now suppose 4 or 5 readers are there. Some of them will definitely finish reading. Whenever a reader will finish reading, he will come out. When the reader will come out, it will decrement the read count. The way we have incremented the read count, it will decrement the read count. Like that, one user will finish and come out and decrement the read count. When the last person will come out, that means no reader is now left on the critical section. How will you know that this is the last person? If the read count is 0. Every time a reader comes out, we decrement the read count. If the read count is 0, that means what? If the read count is 0, that means this is the last user. When the last user will come, it will release the lock and come. It will release the lock and go. So if it is the last user, it will make signal write and go. That means in that room, the girls are there. Whenever, so one by one girl will leave, we are leaving the room. They are decrementing the read count. Whenever the last girl will leave the room, the board that is being written that no entry for boys is being taken. He will take out that board and go. That means now the boys can be allowed to that room. So if the read count is 0, signal of write. So we put signal of write. So write that you have put over here, wait. That means it is 0 now. We make it 1. So that writer can enter at the same time. And we want again this operation to be done for each reader that comes out. Right? Therefore, we put a mutex and we put a mutex over here. So that means more than 2 reader cannot come out at the same time. The gate is not open that multiple 3 or 4 girls will come out at the same time. The first girl will come, it will invoke the wait mutex, decrement the read count, checks for 0, whether it is its own read count is 0 or not, and then it does the signal mutex. That means it allows the next girl to come out from that room. So like that, all the girls will come out and the last girl will release the lock. So that the writer can enter or the boys can enter into that room. Is it understood or not? Is it understood or anyone having doubt?
Sir?
Yes.
Sir, initially mutex is initialized as 0.
No, mutex is 1. Na? Mutex is 1.
Okay.
And write is also 1.
Sir, if we go to the direct to the reader process,
yes,
then first there is wait mutex, so it is decreased to 0.
Mutex is decreased to 0.
Then we increase the read count by 1.
Yes.
Then wait is decreased to 0.
Write is decreased to 0. Right.
Sir, again the mutex is increased to 1.
Yes. See over here. This is supposed
so
to
that again.
Sorry. This is mutex, right? The mutex is 1. Initially, mutex is 1 and write is 1. Now you say, reader is entering. What it will do?
It will decrease the mutex to 0.
It will decrement to 0. Then read count plus plus.
Sir, then the read count is.
So read count is now. Read count is how much? Read count is initially 0.
1.
So it will
increment 0 initially.
So it will increment to 1. Then, so if it is 1, what it will do?
Then, write is decreased to 0.
Write is decreased to 0. Very
it
good.
Can enter.
So who will enter? Read count will reader will enter. The
Yes,
reader will enter. Can writer enter now?
No.
No. So now what will do? The first reader will enter. First reader has done this. Then what it will do? Signal mutex. Is it or not?
Yes, sir.
So signal mutex means it will make again make it to 1. Then another reader will come.
Yes.
Another reader will come. The mutex it will set to 0.
Yes.
It will increment the read count to 2. Right, already this is not the first reader, so no need to put the right is already 0. So it will again release it to 1. Why this mutex we are taking? That no reader will enter at the same time. No reader will, sorry, no reader
So
will
when the
increment.
second
No
reader
reader
enters,
whenever. Hello.
yes, sir. Whenever the second reader enters, at that time the write is equals to 0, so it cannot enter into the critical section.
No, write is 0 means no writer can enter. Because why it is there? Because while entering, are you checking the write? Are you going for write, wait, write? Are you invoking anywhere? Wait, write you are giving for the first reader only.
No.
Right? So this write lock what you have put is actually for the writer, because while writer is entering, it is checking for this. But when the reader is entering, it is not checking for wait, write. It is not checking for wait, write. Are you getting me?
Yes, sir.
So this is that means the lock is for the writer, not for the reader. You understood? Because while reader will enter,
Yes, sir.
nowhere we are checking for wait, write. This wait, write is just to put lock for the first user, first reader. Correct?
Yes, sir.
Very good. Anyone having doubt? So every time a reader comes out, it will decrement the read count. Is it understood or not? These three are very, very important.
Yes.
Producer, consumer, reader, writer, and another one we'll discuss now, dining philosopher, and one will definitely come in your exam. If you see, you try to understand, I have already explained. Besides that, if you have doubt also, you can again ask me in any of the classes, you can ask. So we'll go for one more classical problem of synchronization. Is called the dining philosopher problem. Dining philosopher problem. See, I am saying some of the lines. Try to understand and remember what is the problem, because solution is nothing difficult. Problem, try to understand. There is a circular table or round table in which 5 philosophers are sitting. Try to understand. There is a round table in which 5 philosophers are sitting over there. And at the center, there is a bowl. At the center, there is a bowl of rice. Correct? There is a center of bowl of rice over here. Each of the philosopher is having one plate in front of them. So this is one philosopher having one plate. This is another philosopher having one plate. So every philosopher has a plate over here. And there is a chopstick to left of the philosopher and right of a philosopher. So for every philosopher, suppose I will take this philosopher, then there is a chopstick over here, there is a chopstick over here. Understood? So if I take this philosopher, there is a chopstick over here and this. And if this is a philosopher, there are 2 chopsticks. If this is a philosopher, there are 2 chopsticks, and this is a philosopher having 2 chopsticks over here. Is it understood? Next point is that the philosophers spend their lives just by thinking and eating. They have only 2 work. These philosophers have only 2 work. They spend their life, the entire life, what they are doing? They are doing 2 things. Either they are thinking. When they are not thinking, they are eating. So when they are eating over, they will again think. But they do not think and eat at a time. At the same time, a philosopher cannot think and eat. So while she is eating, that time she cannot think. Correct? So philosophers spend their life alternating thinking and eating. There are only two states over here. This is actually this is resembles to our resource allocation or how to avoid the deadlock kind of, sorry, how to, the process can be single. If multiple processes are there, limited number of resources are there, whether the process synchronization can occur or not. We'll see over here. They share a circular table, I have already told, surrounded by chairs. I said these are the chairs that are there in front of these philosophers. These are some chairs over here. Correct? So now, one more thing I said, that they spend their life by thinking and eating, and during when they are sitting over here, they do not interact with each other. They do not, even if they are sitting on a circular table, they do not interact with each other. That means they don't talk, whether you have, they don't talk at all. So they do not interact. That means the processes are independent. They are running independently, right? They do not interact with their neighbors. That you remember, right? Occasionally try to pick up 2 chopsticks to eat from the bowl. So somebody, suppose the philosopher one wants to eat. How it will eat? A philosopher can only eat when both its chopsticks are available. A philosopher can only eat when both the chopsticks near to him, that means left chopstick and right chopstick, if both the chopsticks are available, then only the philosopher can eat. Correct? So he cannot eat with one chopstick. Second one says that he will acquire only one chopstick at a time. It is not that he is grabbing both the chopsticks at the same time. What she is doing, she is taking one chopstick, suppose left chopstick, then it will go for acquiring the right chopstick. Correct? So to eat, each philosopher requires 2 chopsticks, and at a particular time he can take only one chopstick at a time. There are total, how many chopsticks are there? You can see over here, there are only 5 chopsticks and 5 plates. Correct? So it is not that the 5 people have 10 chopsticks. It is not like that. So they are sharing the chopstick. So now what you have, in case of these 5 philosophers, the shared data is the bowl of rice they are sharing, and the 5 chopsticks they are sharing. These are the resources, the common resources that share. Bowl of rice which is at the center, 5 chopsticks which are kept near to them. And with every philosopher, only 2 chopsticks are near to them. Is it understood? Is it understood up to this? The problem you have to explain actually. There is a circular table. The philosophers are sitting surrounding the table. A rice bowl is at the center of the table. Philosophers do not interact with each other. So philosopher has 2 states, either thinking and eating. Whenever philosopher thinks nearby him, but it will acquire one chopstick at a time. If second one is not available, it will be in waiting state. So the application is concurrency control, allocation of several resources among several processes in a deadlock-free and starvation-free environment. How it will give the solution so that deadlock will not occur or starvation will not occur. So what is the problem over here? Problem is that whenever philosopher gets hungry, he or she tries to pick up the closest chopsticks if they are free. That means one can only eat one whenever one gets hungry, it wants to eat. It will try to get its left chopstick. Understood? If these two are free, because this may be taken by the philosopher 2 and this may be taken by philosopher 5. So if these two are free, then only the philosopher 1 can eat. The philosopher 4 can eat if these two are free. So we can also number them as 1, 2, 3, 4, like the chopsticks are also being numbered. The chopsticks are also being numbered, right? So whenever philosopher 1 wants to write, the chopstick 1 and the chopstick 5 has to be free. When the philosopher 4 wants to write, chopstick 3 and 4 has to be free. So when the philosopher gets both chopstick at a time, he or she eats without releasing the chopstick. So whenever he or she eats, he eats using both the chopstick, and during she is eating, she will not release the chopstick. She will not release the chopstick. She will go on eating like that. Correct? So when she finishes, puts down both the chopsticks. Whenever the eating is over, she will put both the chopsticks down so that others can avail. Is the problem understood up to this? We'll go for solution now. Is the problem understood, or anyone having doubt up to this? Is it understood?
Yes, sir.
Okay. So can you tell me, propose any one solution? Suppose one wants to eat, what it should do so that he will able to eat, and its neighbors should not should have to wait till the one has not been finished its eating. Just look over here. What will do over here? When someone wants to eat, that means he has to put lock on the chopstick. He will get the chopstick, then only he can eat. So what we'll do over here, we'll take semaphore chopstick of 5. That means I have not one semaphore, I have 5 semaphores over here. I have 5 semaphores over here. 1, 2, 3, 4, 5. As these are semaphores, so each are initialized to 1. Each are initialized to 1. Correct? So first one for the first chopstick, this is for the second chopstick, this is for the third chopstick, this is for the fourth chopstick, and this is for the fifth chopstick. These are, we'll take 5 semaphores. Chopstick of 5, chopstick of 0, chopstick of 1, chopstick like that. So the philosopher tries to grab a chopstick by executing the wait operation and release the chopstick by using the signal operation. Whenever it will take, it will put wait, and when it finish, it will use the signal. So if the philosopher 1 will take, it will put the lock on what? 1 and 5. 1 and 5, because these two are near to that philosopher. So it will put lock on chopstick of I, and it will put lock on chopstick of I plus 1 modulo 5. So chopstick of I and chopstick of I plus 1 modulo 5. So actually it is being numbered from 0, 1, 2, 3, 4. Anyway, so that is the way it is being written over here. So it will put a lock on the ith chopstick. That means, suppose this is a philosopher, it will put lock on the ith chopstick, and it should put lock on I plus 1 modulo 5 chopstick. So if it will put lock on this, so it will put lock first with the left one, then it will put lock on the right one, and then it will start eating. And whenever the eating is over, it will release the chopstick by invoking the signal. So signal chopstick of I, it will release this, and signal chopstick of I plus 1 modulo 5, it will release this. So if it will take a particular, suppose that means suppose it might be taking 1 and 5 at a time, right? So whenever it is taking, when a philosopher is over here, it is putting lock on the ith chopstick and I plus 1 modulo 5 chopstick. I plus 1, 1 plus 1, 2 modulo 5. So this is actually numbered from 1, 2, 3, 4. It should be numbered from 0, 1, 2, 3, 4. So that in the 0 and 0 plus 1, 1 modulo 5 chopstick. In that order, 0, 1, in this way it has to be numbered. 0, 1, 2, 3, 4. So it will put lock on 0 chopstick and 0 plus 1 chopstick. Now for 3, suppose the philosopher 3 wants to get the it. What it will do? Put lock on? It will put lock on 3 and 4, because it will put lock on what? I and I plus 1. It is being numbered like this: 0, 1, 2, 3, 4 in this way. Is it understood what I am saying? Is it understood? Anyone having doubt? Any doubt?
No, sir.
Okay, I think it will log out. Let me take the attendance first. Roll number 2, 3, 4, 5, 6, 7, 8, 9, 18, 20, 22, 25, 27, 30, 34, 37, 39, 50, 55, 71, 71, 73. I am repeating the absentee roll numbers. Roll number 2, 3, 9, 18, 20, 22, 25, 27, 30, 34, 37, 39, 50, 55, 71 and 73. These are absent. So I'll end the meeting now. If anybody, please go through this. If you have doubt, we'll discuss in the next class again.